Hola amigos! Into this video I will combine some of the concepts from the last two ones and explain how to paint a texture on a skeletal mesh. This is a very useful technique that can be used for many purposes, and an obvious one that some of you might want to implement in your game is to show damage on a character with pixel precision, as I'm demonstrating on this poor creature here. Here's a summary of how it works. First, we're going to need an alternative way to get the UVs from the heat, since the easy one doesn't work on skeletal meshes. Once we solve that, we'll make two render targets. One will store the permanent damage and the other will fade over time. Finally, we'll use those two as masks to blend materials and to find out where to spawn some particles. Let's get started. I'm already a couple of steps ahead, but nothing too complicated yet. Here I have a skeletal mesh actor to which I have assigned a new material that so far is just a copy of the default one, to which I added this texture object variable that doesn't do anything yet. We're not going to use it now, but we'll assign it a value in the actor blueprint in a moment. On the blueprint itself, I'm doing a few things on the begin play event. Let's review them. First, I'm creating a 1024 by 1024 render target and assigning it to a variable called rt_damage. Note that if you plan to have a lot of copies of these characters, you might need to reduce the resolution quite a bit. On the other hand, for a single enemy fight, you could even increase it instead. Next, I'm taking the material on the skeletal mesh and creating a dynamic instance of it. This dynamic instance is then set as the current material on the actor before assigning the render target as the texture object variable that I just showed on the material copy. The reason for all these steps so far is to have each paintable actor create their own instances of the render target and material. Otherwise, all of them will share the same textures and you won't be able to have multiple copies of the effect. The other half of this equation is the object doing the painting. Let's check it out. I have a boolean variable that I'm going to set on and off when clicking the left mouse button, which is the control I have assigned to this paint input action. Once I do that, on the tick event, I'm going to check its value and, if true, then call this shootPaint function. This one will be familiar if you followed the tutorial that I posted a few weeks ago, but I'll still go over it in detail. The function takes the current position of this actor and does a raycast in its forward direction, up to the length specified by the trace distance variable. It does that by setting the end position to the start position plus the forward vector times the distance. If this trace finds a hit, then it casts the actor to the paintable mesh class, and if it's a child class of it, then call a function on this actor. That function, called bePainted, is currently empty and we'll see it in a moment. For now on, let's put a print string here to see if the raycast is correct and we only get a text output when hitting our friend here. Later on, I'll offset the start of the raycast a bit so it doesn't come exactly from the center of the screen and it's easier to aim. The important thing is that it seems to be working, so I can move on to explaining a bit about UVs before solving the heat coordinates. Let's open this character texture. The important thing to think about is that every pixel that we render from that mesh corresponds to a pixel in this texture, determined by its UV coordinates, going from 0 to 1 in both directions. We can also know each pixel's position in world space, which means that we can move all of them to a single point, and then arrange them by UV. This whole process is called Unwrap, and it's a very common operation when mapping textures. With static meshes, you don't need to go through all this hassle. Unreal has this option called Support UV from Heat Results, but at the time of making this tutorial, it doesn't work on skeletal meshes. It also has a performance cost, so you might not want to enable it for your own project. Now, if you give me a second, I'll make a quick material to show the UV mapping on this particular character and explain why this is important. I'll just connect a texture coordinate to the color and emissive outputs and put it on the mesh to see how it's mapped. You see, to have more real estate for detail, sometimes texture artists reuse parts of an image twice or more on symmetrical areas of the model, overlapping its UVs. While in theory this is a great practice, in our case this would cause also the painting to be applied symmetrically on those areas. Another common problem is badly shaped UVs that stretch the textures too much, which in our case would smear the results and make them look low res. Thankfully, this model looks pretty good and doesn't have any of those issues. I've already created a material that does the unwrapping. I'll show it to you later so you can copy it, but let me explain what it does before we check its graph. On meshes that doesn't use nanite, we can apply an offset to the location where we paint each of its pixels. If we move all of them the same amount as the negative of their current position, they will all go to the origin. For example, if the tip of this nasty end bit here is at 80, 80, 35, for example, and subtract that value, that pixel will be painted at 0, 0, 0. We can then take that pixel singularity, with all of them concentrated, and add the UV coordinates to it, scaled by the size of the rendered target texture. This will arrange them in a square that we can move then by offsetting with another sum. I've called this material m_unwrapper. Let's take a look at it. Here's the graph. First, there's a subtract 0.5 to center the texture coordinate. Then, this is multiplied by the resolution of the render target, in this case 1024, and then converted into a vector 3D by appending a 0 as z. Then we add the output location, which is an input parameter, and finally we subtract the world position. Applying this to the offset output will do the trick for now, but we'll come back to this material later to add our damage mask. Remember that empty function call that I replaced by a print string on the painter object? Now it's time to go back to that blueprint and put it again on the should paint function. If you didn't create it earlier, do it now so you can add a call to it here. After that, let's jump into the bePainted function and start constructing it. I added two function inputs to it, a vector to receive a hit location and a float to specify the radius. I also added a material interface object variable which we will use immediately to save the current material and be able to restore it later. Get the material from the skeletal mesh object and assign it to this new variable, which I called old material. Note that if your mesh have multiple material slots, you would have to do this for each one of them and also create more render targets and material instances on the actor blueprint when you initialize it. Next, we'll assign the unwrapper material that we just made to this skeleton and set the capture location parameter on it. We're going to unwrap the mesh around its root, otherwise you might have problems calculating the position in larger scale worlds. Add a segVector parameter value on materials and change the parameter name to match the one on the unwrapper. For location, we'll get the world position of the root component and add a vertical offset to it. This last part is not necessary when we capture the material, but we'll avoid set fighting issues with the floor when we test it in the viewport in a moment. That should do it. Now, once I click play and hit the character with the raycast, the mesh should get assigned this unwrapped material, and that should be displayed right where it was in the world. Let's give it a test. Perfect. It is doing something and it seems correct, but let's confirm by putting this side by side with the color texture, so we can have a better view of the mesh in its UV unwrapped form. Cool. Now we have something that looks like a 2D texture, but it's still a material applied to our 3D mesh. That means that we can query the world position for each of its pixels, and then paint those according to the distance to an arbitrary location, like for example a hit impact. Let's go back to the Unwrapper material and update it to do precisely that. Start by adding two parameters, which are going to match the inputs that we added to the bePainted function but haven't used yet. Remember, we used a vector for location and a float for radius. Next, add a sphere mask. You can connect the B and radius inputs to our new two parameters, but for A you will need another wall position. In this case, we cannot reuse the one from the other part of the graph, since we need to set this one to exclude offsets and use the original position of the pixel instead. Otherwise, the sphere mask distance would be calculated using the Unwrap position values. Finally, connect the sphere mask to the emissive output of the material. You can adjust the hardness of the mask to get softer edges, or even add distortion or noise to it, but for this example, I'll keep this graph as it is now. Back on the bePainted function, it is time to set these parameters on the material. We have already set the capture location on it earlier, so just add another setVectorParameterValue on materials and a setScalar1, and then update the parameter names to match the ones on the Unwrapper material. We don't have to worry about setting their values now, we'll just pass them as function inputs once we need them, so just connect them to the function beginning and we'll set them up on the function call, which happens after the painter object's raycast. Remember that you can double-click on any connection to quickly add a reroute node. This is quite useful on these long wires, otherwise they can be hard to follow if they go over every other node in the graph. If we go back to the painter's blueprint, we can get the hit location directly from the hit result and connect it to the node. For radius, I'll set a constant value for the video, but in a game this could be set to a random range value or to a size based on the impact damage, speed or size of the attack, for example. Fantastic, this is exactly what we want. We can shoot rays at the mesh and the Unwrap will show all the pixels within 25 units of the impact. The mesh is still technically in its original location, so we can keep painting and see how the material updates in real time. If you're wondering why the white mask moves even if you're not shooting paint, that is because the mesh is still playing its idle animation, so the distance to the hit point is constantly changing. That won't be a problem for us though, because we'll only capture the frame when the hit happens. I will try to keep all the graphs organized, so they are a bit easier for you to copy if you want to replicate this example. Give me a moment while I add a couple comment boxes to the final Unwrap material. To save this unwrapped mesh into our damage render target, we cannot just do it with a canvas paint like we did in a previous tutorial, because this is still mapped to those UVs on the mesh even if we are seeing it as a flat square on the ground. However, the solution is thankfully not too complicated. We can add a scene capture component to the actor blueprint and get a top-down view of the unwrapped mesh that we can safely store. Let's do it now. After adding the component, rotate it so it faces the ground. Also, you will need to turn it counterclockwise 90 degrees, and even if you don't see me doing it here, set the rotation to be in world space. The Unwrap is always aligned to the X and Y world axis, so the last step will avoid problems when the character rotates. Set also the projection type to orthographic to get a flat view of that mesh. Next, find the primitive render mode property and set it to use show only list. We'll create this list on the blueprint in a moment, which will make the capture render only the character and nothing else on the view. We will have to make a couple more changes to this component later, but for now head over to the Blueprint's Begin Play event to add some new nodes. I'll add a sequence to keep the graph a bit cleaner, but you can add them at the end instead. First, we need to create the actor render list and pass it to the scene capture. In our case, this is gonna be an array containing only a reference to itself. Next, we'll set the texture target property on this scene capture component to be the rt_damage render target that we instantiated earlier. And the last change on the component properties is to disable both the Capture Every Frame and Capture on Movement checkboxes. We just want to take a snapshot of the texture during the instant that the mesh gets the Unwrap material assigned, and not constantly. Notice that I also changed the resolution of the orthographic viewport to match the render target, which I forgot to mention earlier. Now we have to update the bePainted function in two different ways. First, after setting the Unwrap material, we'll tell the component to get a snapshot using the Capture Scene node. Afterwards, we'll have to restore the previous material on the mesh, which we conveniently saved as the variable old_material. And note that since all these operations happen within a frame, this material change will never be actually visible in the main pass, so you don't have to worry about that. Since the Unwrap is no longer visible, it is time to update the character material to show the mask. We will just sample the render target texture and output it as emissive value for now. We'll figure out more creative ways to use this later on, but this will allow us to see what we're doing when we test it. This is pretty cool. Since we are using a spherical mask, the heat is not simply projected from the camera and affects the mesh in 3D. And we could use this as it is now, for example to emit particles on impact or some effect like that, but we are going to change it to be an additive mask so it accumulates over time. To do that, the only change we have to make is the composite mode on the scene capture component 2D, which is set to override by default. After making that little change on the component properties, we can give it another test to see the mask working as intended. We're going to make 3 different effects with this mask, but before that, let me diverge for a minute or two and talk about mesh collision. If you've been following this tutorial along, you might have noticed that your mask has gaps, some areas where no matter how you aim, they seem impossible to paint. On the other hand, you might have the opposite problem. The mesh is being painted when you aim just close to it. Both of these issues are caused by how collision works. Since character meshes can be very complicated and ragdoll physics would be too expensive to calculate using all the triangles, they usually use simplified shapes, the most common one being capsules. And remember, we're calculating the mask using the distance between the physics hit location and the pixel location, which will not be the same. There are a few workarounds for this issue. The first one, and possibly the way to go, is to spend some time adjusting the collision shapes to match the mesh as best as you can. You can also enable per triangle collision on the asset details panels of the mesh, but this also has a cost, and might cause some other problems in your game. Finally, you can always increase the radius of the sphere mask, but again, that might not work for your particular use scenario. Let's spend some time off camera later on tweaking the shapes and adding 1 or 2 more until I can still get full coverage without using a giant brush, but don't worry about it. Coming up next, we'll head back to the mesh material to see how to use this mask to swap between 2 textures. Earlier on, I made this cheap variation of the original texture by overlaying over it some distorted photos of different types of meat in Photoshop. In this example, I'll just swap the base color texture, but you can extend this to the rest of the material outputs and have a completely different second look. For example, this guy could be a robot and reveal a complex metallic material underneath. The easiest way to blend between the 2 texture samplers is using a linear interpolate node. We want to avoid overexposing the second image, so we need to add a saturate before the layer node to constrain the value between 0 and 1. Next, we can remove the emissive and replace the base color output before going back to the viewport and testing these changes. Although the quality of my texture is very questionable, the effect seems to be working. In a big game production, character artists would probably make a full set of textures from scratch for each different layer. And something that I haven't mentioned before is that at the moment our render target only contains grayscale values, but nothing stops us from using the different texture channels to encode other information. For example, you could use each RGBA texture channel to save a different value for each damage type in your game, or store the velocity of the physics collision that caused it. Another fun thing that we can do to mess up this poor monster a bit more is to offset the mesh inwards in the damage areas to make it look like it is being eaten away by this effect. We will do that by getting the vertex normal, multiplying it by the negative of the maximal distance that we want the mesh to shrink, and finally multiplying it again by the damage mask before outputting it as wall position offset. Note that this will break most meshes if you set the distance too high. You could drive the maximum of that value with a texture or use a combination of normal and parallax mapping to simulate the effect. I added the wrong normal. Pixel normal is not readable in this context, so we cannot use it. Once that small mistake is fixed, we can try it again and see how the updated effect looks. As expected, the effect breaks a bit on the face, and the legs should not be just slim red dirty pants if we plan to shrink them as well, but that part is just the bad texture. With some work, this type of effect can produce really amazing results. Previously, we saw how setting the scene capture render mode to override can give us a mask with the instant hit, while if we set it to additive, this mask accumulates over time. Next on, we're going to see how to make a mask that continuously fades over time using a second render target and a material stage. Afterwards, we'll use this second mask to make a couple of different effects. We'll start this part of the tutorial by creating a second render target and assigning it to a new variable which I called rt_damage_temp. Afterwards, we need to remove the part where we assign the render target to the capture component. We'll need to do that twice now, but on the bePainted function instead. Let's get that done. Right past the nodes where we're setting the material parameters, this is the order of operations. First, we'll assign one of the render targets and make a scene capture. Then, assign the second render target and make a scene capture again. For now, that won't do anything other than waste precious memory, but we'll give this second render target some use in a moment. Create a new material and call it something like damage fade or similar. This one will be an extremely simple material. It will just take a texture object parameter, sample it, and multiply the result by a number lower than 1. This will fade the texture just a little, but once we apply it to the same render target over and over again, it will make it fade over time. You can think of the material stage preview as if we were looking at one frame of the process alone. We'll need to make a dynamic copy of this material to apply it. Right after we create the main material instance, add another create dynamic material instance, but this one without a mesh target. Set the parent on this one to the damage fade material and reconnect the nodes appropriately. Afterwards, we'll need to set the texture object property on the new instance, assigning it the temp damage render target as value. Let's also add the second render target to our main character material as a texture parameter, so we have a way to pre-visualize it. Same as before, we'll keep it super simple. Just sample the provided texture and put it directly on the emissive channel without any other changes to it. I'll keep the parameter naming consistent in this material and call the new one rt_temp damage. Now we can go back to the previous event graph and set the runtime value to the second render target. By the way, I think one of these connections might be wrong, but don't worry too much. I'll come back to it in a moment with a reorganized graph and show the whole thing a bit better. In case you're curious, I have assigned the second render target twice to the instance damage fade instead of assigning it once to the character material. Okay, so the second layer is showing up correctly on the target. It doesn't dissipate yet because we're still not passing it through our fade material stage, but we'll do that next. If you want a deeper tutorial about that topic, check the video I posted a few weeks ago where I use this technique in multiple ways. And here's the fixed graph, with a couple of reroute nodes to see the connections better. But in short, the character instance material is using both render targets, while the fade stage only uses the second one. I'm going to keep this next part a bit simpler and run the material stage every frame on the event tick. If you have multiple paintable meshes at the same time, you might want to run this every few frames and only when a character is damaged, to optimize things a little bit. Those who went through the other video that I just mentioned will be familiar with what's coming up next. Using the temp damage, we'll add both a begin and end draw canvas to render target, and sandwich between those two nodes a draw material call. This one will paint the damage fade material that we instantiated, and which I will promote to a variable now to keep the graph a bit more organized. The parameters on the draw material can be left as default, but don't forget to connect the size from the begin draw canvas to the screen size input. At the risk of sounding repetitive, let me recap once more. When we paint on a supported actor, its mesh is unwrapped by a material that also draws a mask based on the paintbrush position. This material is then stored in two render targets. One of them accumulates while the second one fades over time. Those two render targets are finally used to add different effects to the material used by the actor. And this seems to be working, so let's add some glow to this material, and this time using some noise to make the mask more visually interesting. I didn't pick up the best noise for this job, but I think that it will work out fine. An obvious improvement would have been to pan the noise and possibly distort its UVs a bit. Even a better, but more complicated one, would have been to use the vertex normal to pan the noise in the direction of the mesh, but it was already late when I was recording this video and I didn't feel like being that fancy. Anyway, what I did here was to do a step between the temporary mask and the noise texture, before multiplying it by a very bright red-orange color. All of this went back to the emissive output to add that hot glow on impact. Nice, I think that the glow helps hiding the texture swap and the noise is making it look much more organic. And I know, this could look a lot better, but for 30 minutes of tutorial, mostly focused on the technical bits and less on the art, I would give this a decent score in my book. And we're not finished yet. In the last part, we'll sample one of these render target textures in a Niagara system, using the mask value to emit particles only from the glowing areas. Here's a Niagara system that emits source particles from a skeletal mesh, which are then sampled by another two emitters, one of them for the smoke and one for the embers. By the way, if you want to know more about sampling skeletal meshes in Niagara, check my previous video where I show 6 different uses for this technique. Here, the source emitter is also sampling the temp damage texture and killing any particles where the value is below some threshold. This is the system with the kill module disabled. This texture object still needs to be assigned in the actor blueprint. Let's do that next to finish the tutorial and check the completed effect. We'll only have to do this once in the begin play event. Add a set Niagara variable, texture, and set the Niagara component in the actor as the target. Then, name the variable to match the one in the system that you're using, and finally, feed it the temp damage render target texture as the last input value. I won't go over the full details of this Niagara effect in this video, but for those who want more particles in their lives, I'm working on a tutorial that will surely make you happy. That's it. That's all I had for you today. I really hope that you had as much fun as I did. If you stayed until the end, thank you for watching this tutorial. Post a comment below if there are any particular visual effects or shaders that you want to see dissected by me. And if you like this content and want to see more like it, don't forget to subscribe and give it a like. See you next time!